Chemical bonding, resonance structures. Individual Lewis structures in cases where two or more Lewis structures are equally good descriptions of a single molecule. That's the definition of a resonance structure. To describe these structures, both are written and use a double-headed arrow to indicate that the real molecule is an average of the two structures. The true structure is considered a blend of the two or more structures that may be involved. All bonds are considered equivalent in length in resonance structures, an intermediate between single bonds and multiple bonds that exist in the molecule. In resonance structures, the order of bonded atoms must remain the same. The only difference in resonance structures is the arrangement of the electrons. So let's consider ozone. If we look at ozone, we know there is, in this particular molecule, 3 oxygens, each with 6 valence electrons. So 3 times 6 is 18 electrons total that we have the ability to use, which gives us 9 pairs of electrons to work with. So if I was going to draw a structure of ozone, I might say one looks like this. Oxygen, 2 bonds coming off, oxygen, and oxygen. And if I filled in all the lone pairs on my oxygen to my left, which would be 3 lone pairs, and an oxygen on my right, which would also three lone pairs, and then also filled in the lone pairs of oxygen that would be on the central atom, I would ultimately be using 10 pairs of electrons total. That means I'm going to need to have a double bond here. So if I do a double bond in between these 2 oxygens, and then I add in lone pairs to everywhere else, lone pair, lone pair, lone pair, and then give myself one more lone pair off my central atom, if I count up the number of electron pairs either involved in bonding or in lone pairs, I'd find out that I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pairs. So I could draw another structure of oxygen. So here is my central oxygen. I'm going to have an oxygen off over here and an oxygen off over here. And again, I'd run into the same situation that if I gave lone pairs to the 2 outer oxygens and 2 lone pairs to the central oxygen, I would still have 10. So now, to make it different from that other version of ozone, I'm going to put my lone pair over here and put a lone pair, 1 lone pair up here, and give this oxygen its 3 lone pairs. So each oxygen has its full octet. But these are 2 resonance structures of each other because they have different arrangements of the electrons. So in ozone, the molecule always has 2 equivalent oxygen to oxygen bonds whose lengths are intermediate between the lengths of an oxygen-oxygen single bond and an oxygen-oxygen double bond. Ozone is often described as having 1.5 bonds. Draw 2 equivalent structures for the formate ion HCO2-1. So the first thing that we need to do is figure out how many electron pairs we have to work with. So in this ion, we have 1 hydrogen with 1 valence electron. So that's 1. We have a carbon, 1 carbon, 4 valence electrons. So that's 4. We have oxygen, 2 oxygens times 6 valence electrons, which is 12. And if we add these all up, we get 17 electrons, but we have to remember this little -1 charge over here, which means, yay, we get to add on 1 more electron, which gives us an even number of electrons to work with, which means we have 9 pairs of electrons. So I'm going to try to draw the structure of this in the format that they give us. So for my first structure, I'm going to draw a hydrogen connected to a central atom of carbon, an oxygen over here, and let's put another oxygen going down. Now, if I put lone pairs around my bottom oxygen, lone pairs around my oxygen off to the right, and another set of lone pairs on the carbon atom, I am going to have more than 9 pairs, which means I need to have a double bond. So I'm going to put a double bond right here. I'm going to give this oxygen 2 lone pairs, and I'm going to give this oxygen 3 lone pairs. And if I do this, I find out that I have 9 pairs of electrons either involved in bonding pairs or non-bonding pairs, and that works for this ion of formate. So to be perfect, we should put a charge of -1 around the whole thing. But again, we need 2 equivalent resonance structures, and we can't change the order of how we've organized our elements, just how the electrons are distributed. Therefore, I'm still going to have a hydrogen, a carbon, an oxygen, and an oxygen down here. But instead of having the double bond off to the right, I'm now going to have the double bond going down. So this oxygen is just going to get 2 lone pairs. This oxygen off to the right is going to get 3 lone pairs. So I have distributed the electrons differently, but the order of the elements is still the same. So now I'm going to have this whole thing having an overall charge of -1, and then I'm going to put my double-headed arrow in between the two saying, hey, these are 2 resonance structures for the formate ion.